For today, I will talk about Avalanche Consensus and the family of Snow Consensus protocols, and you will see an example of Polymorphic Consensus, where a chain changes from Tendermint Consensus to Avalanche Consensus while running through an on-chain governance process. And to set the stage, this demo is executed on our Mythos chain, which is a chain built on top of the Cosmos SDK with WebAssembly smart contracts that supports various virtual machines from Ethereum VM to CosmWasm, JavaScript, Python, AssemblyScript, and more. And this blockchain has its core blockchain features implemented as smart contracts, and the consensus protocols are also smart contracts. So this makes it really convenient to change consensus protocols by governance. In previous videos, I already demonstrated a RAFT consensus change to another RAFT consensus contract that I deployed with some parameter changes. And I also demonstrated a change from RAFT consensus to a Tendermint consensus contract. And today you will see from RAFT consensus to Avalanche and from Tendermint to Avalanche. And of course, you can always go back to the previous consensus, so this can be a bidirectional transition. But first, I will explain Avalanche Consensus, which is actually a family of consensus protocols named Snow. And we will have Slush, Snowflake, Snowball, and a simplified version of Snowman. And I have made finite state machine diagrams to both explain the mechanism, but more important, these are actual smart contracts that can be executed on Mythos. This Avalanche Snowman diagram produces a JSON object that is then interpreted on-chain by a finite state machine interpreter contract. So what you see here is exactly what the chain executes. But before Snowman, we start with Slush. Slush, Snowflake, and Snowball, all three are described in their binary form in the Avalanche white paper. Slush is the core, and we have three main states: the uncolored state, the red state, and the blue state. And I've also added some sub-states here, limbo, active, and final, to show whether the process of color selection is finalized or not. So each node starts as an uncolored node. And when a node receives a colored transaction, like a red transaction or a blue transaction, then it colors itself with that color and transitions to either the red color for the red transaction or the blue color for the blue transaction. And the process inside these two colors is the same for either color. First, the node needs to determine what color will the network adopt. So what happens here, and we will look at the active phase. The node starts to query other nodes. So first it selects a random sample of other nodes from the network, and the number of nodes is sample size, which is a protocol parameter. And for this, the node sends these selected nodes a query with the red color and expects a response from them with their selected color. Of course, if the other node is in an uncolored state, when they receive this query red event, they will also respond with the color red and also transition to the red state. Now, if the other node is already red, it just sends the response with the color red. If the other node is blue, it just sends the response with the color blue without doing anything else, any other action. So now, after we get all the responses from the other nodes from the selected sample, then we see what the majority color is. And we calculate the majority based on the alpha threshold, which is another parameter of the protocol. And we also increment the round counter. Now, this entire process of determining the color ends when this round counter is equal to a protocol variable that sets the number of rounds that must be done. And you will see it in the white paper as M. So after M rounds, we will have our result. So let's look what happens if the majority color here is blue. Then our color is reset and we enter blue here and we repeat the same process. If our round counter has reached the value of M, then we get to our final color and everything stops. And here, if the majority is still red, then we re-enter this red state and redo all of this process. Again, we first enter the limbo state, we check if the rounds counter is lower than M. If it is, we repeat the sampling process. If not, we have reached our final color. So note that regardless of how many times the majority color changes here between red and blue, when the round counter reaches the M value, the node finalizes the color. So the protocol makes sure that all nodes at least can reach a final state, even if they may not reach the same state if we have malicious nodes in the network, because this is a sampling protocol. So the next protocol, Snowflake, introduces another concept. Now, Snowflake has Slush as basis, but we do not need those substates for red and blue anymore, and you will see why. Again, we have the uncolored state, the red state, the blue state. And the mechanism is very similar. So we will focus on what happens after the random sampling in each of these states. So let's say we are again here in the red state after we have received either a red transaction or a red query. And we have already sampled the network and we have calculated the majority color of this round based on the alpha threshold. And let's say that this time we got the color blue as majority. In this case, the rounds counter is reset to 0. So again, we start the random sampling in the blue color, but from a rounds counter of 0. If the majority color was actually red, then we increment the rounds counter and re-enter the state. If the incremented counter is still lower than the beta threshold. Beta threshold here is a protocol parameter and we can find it in the white paper here. So the difference between Slush and Snowflake is that Snowflake, instead of finishing the protocol when the rounds counter reaches M, now resets the round counter each time there is a color change, either from red to blue or from blue to red, and only finalizes a color after beta successive rounds where that color has reached majority, has won majority in the random sampling process. So instead of stopping after, let's say, 5 rounds, regardless of how many times the majority changed, now we stop only after we get 5 times the color red, for example. So this protocol has a greater chance than Slush to determine true consensus. But it can also be gamed by malicious nodes who can delay the consensus finalization by resetting the rounds counter with a different color each time. And this part is solved by the third algorithm, Snowball. Now, Snowball is like Snowflake, but instead of directly changing the color when a majority is reached here, for example. In the red state, we ran the random sampling algorithm and we got a majority of nodes saying that their color is blue. So instead of changing to blue immediately, now we have something that is named confidence. Each color has its own confidence. And we increment the confidence of the blue color here, we reset the rounds counter, and I introduced a temporary state, which is a limbo state for red, because we only change to the blue color if the blue confidence is greater than the red confidence. Otherwise, we have an else here, we increment the rounds counter, and we re-enter the red state and continue our processing, just like before. And of course, the same process is followed if we are in the blue color and our majority is red. We have the confidence for the color red here, and the process is symmetric. So now for Snowball, let's assume the color red won in 3 rounds. And now we are in the 4th round and the blue color wins. We do not change to blue because the confidence in blue now is 1, but the confidence in red is 3. So we remain on red and continue the process until the counter variable is equal to our beta protocol parameter. Now, I also have some generalized versions of these protocols, and this is for any color, but the complexity of the generalization is not tackled in the diagram itself, but it is tackled in the underlying implementation of the functions and the data structures, so our colors will be indexed in a mapping and they are referenced by a variable named color instead of the actual color. Now, Avalanche also has a Snowman protocol for blockchains with linear ordered blocks, and they solve the multiple colors problem through an algorithm that reduces the possible states until they get to a binary decision, like red and blue. And also they have a supra algorithm where instead of letting all nodes propose blocks like usual, in case of a network congestion, only a selected group can propose in a determined order. But I will not do this instead. This is a simplified version of Snowman where we can have multiple competing blocks at the same time, but we just do not care about this issue now. Instead, we just want to use what we learned from Slush, Snowflake, Snowball, and Snowman and implement a rudimentary version of it that actually works for a blockchain. And instead of colors, we have blocks with transactions. And in this version, we propose a block each time we receive a new user transaction. So we have the validator state of a node and the proposer state. Once we have proposed a block, we transition to the proposer state and we do the random sampling process. And now the color of the block is the block hash. So each competing block hash has a confidence counter. The validator is the uncolored node and the proposer is the colored node. And now whenever we are in the validator state and we receive a query from another node, we also check whether the block was already finalized. And if yes, then we just return that finalized block. And this is abstracted away in the send response function. If the block is new, we take it and our node transitions to proposer. And here we do our random sampling. And if the majority value is lower than our alpha threshold, we actually reset the rounds counter and resample. if our alpha threshold is reached, then if another block hash got the majority, we are in a temporary limbo state, just like in Snowball. And now we look at the confidences for each block hash. And we only change the proposed block if that block's hash has a confidence that is greater than the hash that we started with. Otherwise, we just increment the rounds counter, we check to see if we have reached the beta threshold, and if we have, then we finalize the block and get back to the validator state, ready to propose another block. On this other branch, if the majority is still the proposed hash that we proposed, then we increment the rounds counter and go back to resample if we have not reached the beta threshold, or we finalize the block and transition to the validator state where our rounds counter is reset or confidences are reset for the next block. And here we just have a mechanism for starting, stopping, and restarting the consensus protocol, and you will see this part next because this diagram will actually be executed on a blockchain. And now that you know what to expect, let's go on with the demo. Here we are in RAFT consensus. So we have a blockchain with two nodes. One of them is a leader and the other one is a follower. And we can also see this in the Explorer. So only node 1 can propose blocks, and this is the leader node. All of these consensus algorithms, RAFT, Tendermint, this new Snowman-like consensus protocol, exist already deployed on this chain. So we just need to make the governance proposal to change from RAFT, the one that is running now, to Snowman. And I will send this transaction. This transaction is actually a governance proposal that will use this contract address, which is the contract for our Snowman-like protocol, and it will register this address for the consensus role. And we have a title for the governance proposal and a description, and we will just send this transaction. And we should be able to see this transaction included in a block, so we see the new governance proposal here. Now we can go back and we will cast our vote here. And we see the vote. Now this governance proposal will run for 2 minutes, and then we will see the consensus change. So let's leave so we can see the blocks in the Explorer here. Now, as in previous videos, changing the consensus is done by the current consensus contract, meaning the RAFT protocol contract in this case. When a consensus event change is received after the current consensus finalizes a block, then the new consensus contract address is picked up and the setup and start events are triggered on the new consensus contract. The new consensus contract gets all the information it needs from the old contract stops itself, and a new go routine with the new contract is started. And we should be able to see this process starting here any moment now. Okay, the process has started. And we already see here that the Snowman Consensus was pre-started. And now the chain seems stopped. But this is because our Snowman-like consensus protocol doesn't actually produce blocks unless a transaction is sent. But let's look at what happened here. So block 84 was finalized, and we see the proposal was tallied, our governance proposal, and it passed. And then the new consensus contract was picked up with this address. We set up the new consensus contract. We copied over whatever data the new contract needed. Then we stopped our current consensus contract. We finalized the block, and then we started the new consensus. And then these are a couple of other processes from the old consensus that have been stopped. And this process also happened on our second node. So now we can send a payment transaction and see the first block created with the new protocol. So a new block was finalized, 85. And we can see this block also here with the new transaction. So let's look at what happened. We received the transaction. This node received the transaction and started a block proposal, and this is the hash of the new block, and the height is 85. So now we are sending the random sampling query to our random set with the proposed hash. Now the round counter is 0 and our sample size is 2, but we only have 2 nodes here. So we are going to only send this query to the other node. And these are the options we have for the next block, and we only have one option. So then we calculate if the majority, which now has a count of 2 because the other node actually responded. So we check to see if 2 is greater than the alpha threshold, which in our case is 2, and it is. So we increment the counter, and we again repeat the random sampling process. We don't have enough nodes to actually see the random sampling here, but we move forward. We do the same things, and now we have reached the beta threshold, which is 2. And our rounds counter is also 2. So we can start the block finalization. And we also index the transaction. This is something happening in the blocks smart contract, the contract where we store blocks and transactions. And we have some other logs here because this other node does its own query requests. So let's see where it starts. It starts here by trying to process the if block not finalized guard. And if you remember, we are talking about this guard. So the node received a query, tries to see if the block was not finalized before, and if it was not, it will go and transition to the proposer state. So that's exactly what it does. It has transitioned to the pre-proposer state for now, and also it sends the query response back to the other node, and it's just saying that it has accepted the proposed hash. The round counter is 0. And again, it sends a second query response to the other node. And actually now it's time to do the random sampling for itself. So it sends a query to our first node. It actually receives a response because they agreed on the hash, the proposed hash. And we go to 2 rounds of random sampling, and then it can start the finalization of the block with height 85. And we can continue and send another transaction, and now we are at block 86. Now, this is a simplified version of Avalanche-Snowman, shown on only 2 nodes. Ideally, this algorithm should be shown on at least 20 nodes with at least 2 competing blocks to actually see the network sampling and propagation. Also, this demo does not tackle what happens when several blocks are proposed at the same time by different nodes. And similarly, we can change from Tendermint consensus, where each validator can become a proposer based on the stake, to our Snowman-like consensus. And we can see the nodes here being finalized by both node 0 and node 1. And we will do exactly the same process. So we will send the governance proposal registering our contract as our Snowman contract on the consensus role, and then we will be sending our vote. But let's look here in block 12. We already have our governance proposal, so we can see it also in the governance tab. So now we will also vote. So now we can see our vote, and we have again 2 minutes to wait. And the process was started, and we are already in the Snowman protocol. So we can see that block 20 with height 24 has been finalized. So that's the block that included the governance proposal that has passed. And we are setting up the new consensus protocol with the setup phase that we already know and starting the new contract. And we are again in the same position that the node, the chain will only continue if we send a transaction. So let's send a payment transaction, and we see the block being finalized to block 25. And again, another transaction, we are at block 26. Today you have seen a chain with polymorphic consensus, where consensus protocols are implemented as finite state machine diagrams. This is the best playground to create blockchains with different consensus protocols and compare them.